Hey guys, we're going to do a comparison problem today. This question is, let's see, it's the very end of section 10.1. It's on page 5 of your chapter 10 packet. I'm going to read through the question real quick and then we're going to come up with a plan of attack. This is another full, write-up, free response type of question. Very, very common type of question to see on the AP. So I'm going to go through slowly everything you need to do in order to earn full credit on an AP exam, on the chapter test for this unit, etc. So what we've got here is GM wants to help its employees stop smoking. And so they've got these people randomly assigned into two different groups. One of the groups has a cash incentive to quit smoking, and the other group has no cash incentive. And we're trying to decide here, the way that this question is worded, do the results of this study give convincing evidence? That's your clue that we're doing a test. Keep in mind that in this chapter, you're going to be doing tests, so writing hos and ha's, null hypotheses and alternate hypotheses, and actually coming up with p-values. And there's other questions that we've done already in class and that we will continue to do that don't say, do these give convincing evidence, but it'll say something like estimate or create an interval, which means you're doing a confidence interval. So this is two chapters kind of combined into one with two different populations. So in this case, we're doing a test because of the way the question is worded. Do we have convincing evidence that giving a financial incentive helps people actually quit smoking? So what I have here in this question is I have a lot of important info, I guess. Let's talk about this 15% right here. This is going to be my p hat 1. I have a 5%, which is my p hat 2. I have this number, which means because they were divided into halves, that means that I have two different ends. That's my total, 878. So read the problem carefully. That means I have 439 people in each group, the cash incentive group and the other incentive group. So I'm going to put each group. We do have a lot of info here. And then again, like I was just previously explaining, do we have convincing evidence? That means we're doing a test. So I'm going to write test. Oops. So this is all the pulling pieces out of the problem so that we have the data, we've got it organized. Notice how this $750, that's just a detail, that's not an actual number I'm going to use in my math. But I need to decide, first of all, if this is a one-sided or a two-sided test. So the way that this question is worded is, does a financial incentive help? Basically, is the one group greater than the other group in terms of the percentage of quitting smoking? So this is a one-sided test. Remember, one of the most common problems or errors when doing a test is if it's a two-sided test, forgetting to double the p-value at the end because it represents the left tail and the right tail of the normal curve. So just be careful about this, or the t-distribution if that's what it is also. This one's a one-sided, so we don't have to worry about doubling the p-value. So there's a lot of info here that you need to lay out your plan before you even start writing. So remember, state, plan, do, conclude, and there's a lot of stuff that goes into the state and the plan category. So I first need to name my two populations. So I've written out my two populations. Just be specific when you're writing out your two populations and what the P1 and the P2 stand for. I'm designating my P1 just because that was the first number that I noticed. That goes with my P1 hat. Those are the financial rewards group, the people that got a cash incentive. And then the population that this P1 was taken from was all the people in the cash incentive group. So same thing for P2. That's the proportion of people in the not cash incentive group, the people that weren't given any money to quit smoking. The ones that quit, that's that 0.05. And then the population, those people were taken from the group that did not have the incentive. So now it's time to write my ho and my ha. In order to write the ho, I'm going to subtract the P1 minus the P2. And I want to know, since this is a one-sided, I want to know if the P1 minus the P2 actually is greater than 0. That's my alternate hypothesis that I'm going to write. Remember that the null hypothesis is always an equation. So I'm going to use 0, meaning no difference between cash incentive and no cash incentive. Or is it actually greater than 0 when I do the cash incentive people minus the no cash incentive people? So I'm going to write that out. So I wrote my ho and my ha. When I subtract the P1 minus the P2, and it's important to have those defined up here so you can easily see, wait, which one was P1 again, which one was P2. The P1 minus P2 equals 0, you always need an equation with your null hypothesis. And then in this case, since the wording of my question is, does the financial incentive help? That means is P1 greater than P2, basically, or when I subtract them, do I get a number bigger than 0? This indicates no difference. That means when you subtract them, the difference is 0. And then this means that the cash proportion is greater, the cash incentive people. That's the way that I have it worded here. Keep in mind that the textbook and other textbooks will sometimes write it like this. This is also acceptable if you'd like to write your ho and your ha like this. P1 equals P2 or P1 greater than P2. It's a little bit less writing. I tend to use the equation with 0 and greater than 0 though, but either way you would get full credit for that. That's fine. So now what I need to write out is what kind of a test am I going to use and why. So here's what that statement looks like. Since we're testing a claim, remember that's the wording in the question here that told us what we're doing. We're not estimating something. We're not calculating an interval. In this problem, we're testing a claim. We have ho's and ha's. So since we want to test a claim about, and what are we testing about? A difference in two different proportions from two different populations. So this is the difference between chapter 10 verses 9 and 8. We only had one population in the earlier chapters. Now we're comparing two populations, which is a lot more real life applicable. And because of that, we're going to use a two-sample, because we have two samples, two different populations. A z-test, we're using z as opposed to t because these are proportions. We actually have formulas to calculate, to use with our z-test, and that is how to write out what we're doing and why. Now I have some conditions I need to check: random, independent, and normal. All right, guys, so here's what my condition checks look like. I'm going to zoom in a little bit so you can read it better. But remember, we still got to do random, independent, and normal, just like all the other previous chapters we've done. The random condition is a little bit different for this. We randomly assigned people to each group. We did not randomly select people. Remember, these were volunteers, so make sure that the wording, the way that you explain what's random about this problem, is that it matches what we're given. This is not a random selection. We did not randomly pick people. So be careful about this. We randomly assigned the 439 people into each group. The independent clause, we don't have random selection, so we can't use the 10% condition here. But experimental groups are independent of each other, meaning the cash incentive and the non-cash incentive do not impact each other, as are the individuals. So we're not mentioning 10% condition. We're saying exactly what's independent about this experiment. So be careful about that. That makes this problem a little bit different than some of the other ones we've done in class. And then remember how to do the normal condition check. We got to do the N1 times the P1 and then 1 minus P1. Same thing for N2. We're doing 4 of these because we have 2 different populations. So it's a little bit annoying to check or to walk all the way through. However, remember, we're checking to make sure all of those calculations are greater than or equal to 10. And that helps us decide if our sampling distribution is approximately normal or not. So make sure you mention what is approximately normal about this. It's the sampling distribution of the difference of the two p-hats. Now, finally, we're able to do some math and use our calculator now. Okay, so a couple things to remind you of. We were not given a significance level in alpha, so we're going to use 0.05 since there wasn't one given. It's a good idea to just state that, write it out, so that you know exactly what you're comparing to and so that your AP grader knows why you're using 0.05. There are other textbooks that use 0.1 or something different, so it's just important to state and to write out what significance level you're going to be comparing your p-value to. And then another thing, keep in mind, this is another kind of tricky thing about these proportions, is that when you're doing a test, remember you need to pool your proportions together for your p-hats. So that's why this little C right here, that stands for combined, aka pooled. So what we're doing is we're taking our 2 successes, our 66 people that quit in the first group, which is taken from right here, and our 22 people that quit from the second group, which is taken from right here. And we're dividing it by the total number in each group, 439 plus 439. That gives us a 0.1, and that is what we're going to be using for our pooled proportion when I do my denominator for calculating my z-score. So this part is really important when you're using proportions and doing a test. You have something about that in your reading guide, but you got to make sure that you remember that. That's something that a lot of people kind of forget. So I'm going to actually kind of write this out as I'm talking. So we did this pooled thing because it's going to go here and here, that 0.1 and that 0.1. Here's our formula. Remember, this is on this the formula sheet, but you're doing your statistic, which is when you subtract your first proportion p hat minus your second proportion p hat minus the parameter. And the parameter is kind of weird, but remember our parameter up here is taken all the way from the null hypothesis. We're assuming there's no difference, and we're trying to test that there is one. So that's the 0. No, it doesn't affect the math when you minus the 0, but it helps you stay consistent. This is not the statistic minus the parameter here. The statistic is the difference in the two p hats. And then subtract the parameter, which is minus 0. There's only a few occasions, and we'll do a couple in class, where this number won't be 0, but don't worry about that for right now. And then I'm using my pooled p hat, my combined p hat here and here, and then I still have to use my N1 and my N2 sample size, which both of those happen to be 439. So here's what all those numbers plugged in look like. The p1 hat minus the p2 hat is here. Remember those two p1s and p2s that I was given in the problem were 0.15 and 0.05. And then I'm subtracting my 0. I'm using the pooled proportion here for the 0.1 times the 0.9, and then both of my sample sizes in both groups are 439. So be careful typing that into the calculator. A lot of times that's the hardest part. But that gives us a number of 4.939. And remember what that number represents. That's not our p-value. We're not ready to be like accept or reject or fail to reject or anything like that. Definitely don't say accept. This is the z-score right here. So now I have to do the probability that z is greater than, because remember that this is a one-sided test, so I'm doing probability that z is greater than that number. So that means probability that z is greater than or equal to 4.939. Think about that for a second. What's the probability that something is almost 5 standard deviations above the mean? It's pretty much 0, right? That is my p-value, and that is what I'm comparing to the alpha. So make sure that you're being aware of what it is that you're actually calculating. This was a z-score that we came up with here. The z is that, so I need to figure out the probability that I'm shading to the right of almost 5 standard deviations away from the mean. That probability is 0. And that number, my friends, is way smaller than this alpha significance level. So the p is in fact too low, which means that the HO must go. So we're going to scratch this out, and we are going to favor the alternate. So I wrote out my conclusion. Since that p-value was 0, about 0, which is way less than the alpha, the p is too low, the HO must go. That means we reject the null in favor of the alternate. And then restate what the alternate is. Whatever it is that you are leaning towards or that you're wanting to accept, even though we don't accept the alternate, we reject the null, and that means that we have convincing evidence in favor of the alternate. So I'm using that exact wording. We have convincing evidence that, and then what was the alternate again? The alternate stated in symbols, I just need to convert that to words to add my context, that the proportion of people in the cash group who quit smoking is actually greater than the proportion who quit without the incentive. So we do have evidence that it appears as though the financial incentive does help. Okay, so that is a full write-up, you guys. That was kind of a lot of detail. There's a couple tricky things that you need to make sure that you're aware of here. Make sure that you're pooling for a test for proportions. That is different from when you're doing an interval, so compare that to when we did an interval for this section with proportions. Make sure that you're writing out all of your 2 different populations and your 2 different P's, what they stand for. There are two different ways to write the ho and the ha, like this or like this. And then everything else kind of follows the way that we've been doing in class. These conditions are a little bit different because this is an experiment, so there were a lot of like little tricky things that changed from what we've done in class versus this problem. So bring your questions to class tomorrow. Thanks for watching and have a good night.